Hey everyone, welcome back to Everything is Relative. I'm Mr. K, and today we're going to be doing some topical past paper questions from the Papa Cambridge website on the topic of oscillations for Cambridge A-level physics. Now, as always, I will leave a link in the description for you to download these questions, and they are a good source a good resource for you to practice before your final exam, especially if you want to go topic by topic. And so the topic of oscillations for A-level physics is the last topic on classical mechanics, and mechanics actually. And the topic, although classical in nature, can get quite tricky. It's significantly mathematical. And so today we look at questions 83 to 90, and in the next video I'll do a few more. And the first question I'm going to look at is the first question in the topic. And this, since it's unclear, I'll write it down, is question 83. And this is the subject code for A-level physics 9702. This is from the March 2021 exam. It's question paper 4, variant 2. And this is question number 4 from that paper. And we are told that the defining equation of simple harmonic motion is A is equal to minus omega squared x. And we are asked to state the significance of the minus sign in the equation. Now, the two defining characteristics for simple harmonic motion is that there must be a minus sign, which means whatever the answer is we're going to state, and the omega is a constant value, so omega squared is a constant value, which means the acceleration is proportional to the displacement. So what does the minus sign specifically tells us? It tells us that since omega is some constant value, if I square that constant value, I'm always going to get a positive number. And so the minus sign means the acceleration and the displacement are always in opposite directions. And so that's the way you would write it. Very simple. The acceleration and the displacement are in opposite directions. So when the object is moving far from its equilibrium position, it is accelerating in the opposite direction, accelerating towards the equilibrium position, and vice versa. And so we want to make sure that the restoring force brings the object back to equilibrium, and hence the minus sign makes sure that the object doesn't move off to infinity. It gets pulled back towards the equilibrium position, and hence the minus sign helps us achieve this. The next question says, a trolley rests on the bench, and two identical stretch springs are attached to the trolley as shown in the figure. The other end of each spring is attached to a fixed support. The unstretched length of each spring is 12 centimeters. And the spring constant of each spring is 8 Newton per meter. When the trolley is in equilibrium, the length of each spring is 18 centimeters. The trolley is displaced 4.8 centimeters to one side and then released. And we have to assume that resistive forces on the trolley are negligible, and to show that the resultant force on the trolley at the moment of release is 0.77 newtons. Okay, so this is quite a tricky one. As it stands, each spring is not at equilibrium length. Equilibrium length is, well, the unstretched length, I should say. I shouldn't say equilibrium length because equilibrium is used for the trolley central position. The unstretched length of each spring is 12 centimeters. So both of these springs as they stand are currently under tension. So how do we find the resultant force? Now, there are only two forces acting on this trolley. We'll neglect gravity and the normal force since we're only considering the horizontal forces. And so the net force is the sum of the forces acting on the trolley. One of the forces from the spring on the left is pulling the trolley towards the left. The spring on the right is pulling the trolley towards the right. So they act in two opposite directions. And so at the moment of release, we pull the trolley to one side by 4.8 centimeters. And so one spring is going to be stretched slightly more than the other. And so at that point, the force due to spring 1 minus the force due to spring 2 is going to be the net force on the trolley. K1x1 minus K2x2. And so it's best to just put bigger minus smaller. Now the K values, the force constant for each spring is the same, 8 Newton per meter. And the displacement of the first spring, remember the X value is the extension of the spring. By how much is the spring extended from its unstretched length of 12 centimeters? and that's 0.18, which is the equilibrium length, minus the unstretched length, plus the 0.048 meters, 4.8 centimeters that it's displaced by. And the second spring also has a spring constant of 8. Its equilibrium length is 0.18 minus the unstretched length, which is 0.12. That's the initial extension, minus 0.048, 4.8 centimeters. Since one, we are adding 4.8 centimeters to 18, and the other one, we're removing the 4.8 centimeters from 18. And this x in question here is the extension of the spring, extension over the unstretched length. And so if I do this calculation, what I should find is that the net force is 0.77 newtons. So remember, F1 is the force pointing in one direction, and F2 is due to the other spring on the trolley, which is in the opposite direction. Hence, we subtracted to find the net force. And so it wasn't that bad, it just was the distances that were a little confusing. Initially, each spring is at 18 centimeters, but already that's undergoing tension. We then extend one by 4.8 centimeters and compress the other by 4.8 centimeters. So one gets closer to its equilibrium length or its unstretched length, and one gets further away from its unstretched length. And so at least they gave you a value for the force. Even if you couldn't do this calculation, you could still use it in follow-up questions. And the next question says that the mass of the trolley is 250 grams. Calculate the maximum acceleration of the trolley. Well, the maximum acceleration, A0, is going to be the resultant force divided by the mass from Newton's second law, the mathematical expression of Newton's second law, which is a net force of 0.77 over 0.25. That's going to be the maximum acceleration because it's going to be the maximum extension of the spring at that point. The trolley is not going to go past that point when it's oscillating. Since it's been displaced to that point, it can't go any further. And what I find is this should be 3.08 meters per square second. To two significant figures, 3.1 meters per square second. So fairly straightforward. I have to rearrange the equation for Newton's second law, take the net force, which is the maximum force, which will give rise to the maximum acceleration, divided by the mass, which in kgs is 0.25, and I get acceleration of 3.1 meters per square second. We're then told to use the answer that we just calculated to find the period t of the subsequent oscillation. Now, you have to be really good with manipulating the mathematical equations to save time in this topic. But what I know is A is equal to minus omega squared x. That's given. So I can say that maximum acceleration, which I already know, is equal to minus omega squared times maximum displacement, x naught. But this doesn't really help me because I still need to find t somewhere in this equation. But what we know is that omega, and I can write this down on the side. I should always write it down, just to allow the marker to know that I know the expression. Omega is 2 pi divided by the period, t. And so this becomes minus, remember the minus sign still stays because it's in front of the omega. It's minus 4 pi squared over t squared times x naught, which means we can then do some rearranging if you want to do your mathematics this way. And we get the period t is the square root of minus 4 pi squared x naught divided by a naught. And if you're worried that there's a minus sign in here, remember that if x naught is positive, a naught is negative, and vice versa. If a naught is positive, x naught is negative. So the minuses will cancel off, and we wouldn't have a minus when we're doing the calculation. And so we get this to be minus 4 pi squared times the amplitude, which we know is 0.048 meters, 4.8 centimeters, divided by minus 3.1 meters per square second. If displacement is positive, the acceleration must be negative. And so the two negatives will disappear, and we can do the square root. And we get this period to be 0.782 seconds. Again, to two significant figures, this is 0.78 seconds, the period of the oscillation. So you always have to remember omega is 2 pi over t, omega is 2 pi f. All of these equations for oscillations are quite important, so quite a lot of mathematics to do here. In part 4, the experiment is repeated with an initial displacement of the trolley of 2.4 centimeters, and we want to state and explain the effect, if any, this change will have on the period of the oscillation of the trolley. Well, what I can see is I'm changing the initial displacement to 2.4 centimeters. And the initial displacement originally was 4.8 centimeters. So I'm halving the initial displacement. And so what this means is the net force will be halved. So if I look at this equation, and if I were to calculate the net force again, I wouldn't have to. I can just simply see that since I'm halving the displacement, I'm halving the net force, since the net force is proportional to the extension. And so if I halve the net force, I halve the acceleration. And if I halve the maximum acceleration, then I have a change in the period t. But I'm also halving the initial displacement. So halving the displacement halves the net force and hence halves the acceleration. So the change that I make to x naught is going to be the same order of magnitude of change that's going to happen to a naught. So overall, the period is not going to change. If I double the initial displacement, I'll double the maximum acceleration, and still there's no change to the period. So it turns out that irrespective of my displacement, the amount by which I pull the trolley to one side, the period stays the same. So a very interesting result, and there's nothing from prior knowledge that will just help you understand that this will be the result. But this problem, when you go through the mathematics in the problem, you'll realize, okay, changing the displacement actually in this case will not have effect on the period. So I'm going to say that the net force, and hence the maximum acceleration, is halved. And the amplitude, or the maximum displacement, is also halved. So if I look at my equation for the period, and I can write the equation down if I want to, I can make reference to the equation, but I don't really need to. Hence, there is no change in period. So again, off the top of your head, it's very difficult to answer a question like this. But if you do get a question like this that ends sort of the entire question, a sub-question that ends the entire question, go back through what you've done, look at the mathematics, and see if there's any hints or clues in there that will help you answer this kind of conceptual question. So this was a 9-mark question, a very interesting one indeed. The next one's very similar, and we immediately see that there is a trolley with 2 springs. But we are first asked to state what is simple harmonic motion. And we all know what the definition of simple harmonic motion is. It's the motion in, you can see the repetitive or repeated oscillatory motion, or simply the motion in which acceleration is proportional to the displacement and in the opposite direction to the displacement. I'm simply going to say and in the opposite direction. So a motion in which the acceleration is proportional to the displacement but also in the opposite direction. So a mark for saying proportional and a mark for saying opposite direction. We're then told that a trolley of mass m is held on a horizontal surface by means of two springs. One spring is attached to a fixed point P. The other spring is connected to an oscillator. The springs each have spring constant of 130 Newton per meter, and they're always extended. The oscillator is switched off, and the trolley is displaced along the line of the springs and then released. The resulting oscillations of the trolley are simple harmonic, and the acceleration is minus 2k over m times x, where x is the displacement of the trolley from its equilibrium position. We're given the mass of the trolley to be 840 grams, and we are asked to calculate the frequency of oscillation of the trolley. Now, these are simple harmonic because the oscillator isn't moving. These are two fixed points. We displace the trolley to one side, and the trolley starts to oscillate. And we want to find the frequency of oscillation for these simple harmonic oscillations. And what we know is that the defining equation is A is equal to minus omega squared x. Quite difficult to be given to find the frequency, but we are given other things that will help us. So what this means is if I look at the two forms for the acceleration, the one given and the one I've written down, the thing missing is omega squared. So omega squared is the thing in the brackets. It's 2k over m. And what this means is now I can now find the period, because I know omega is 2 pi f. So 4 pi squared f squared is 2k over m, which means the frequency is the square root of 2k over 4 pi squared m, which is the square root of 2 times the spring constant 130 Newton per meter over 4 pi squared times the mass of the trolley is 0.84 kilograms. And what we get is the frequency to two significant figures is 2.8 hertz. So when you're given the expression and you know the oscillations are simple harmonic, generally whatever's inside the bracket, whatever precedes the x on the right hand side of the equation, as long as there's an a on the left hand side, that thing in brackets will be omega squared. And then you can use that information to find frequency, period, and so on. So that was a nice 3-mark question to start us off. Next, we are told that the oscillator in B is switched on. The frequency of oscillation of the oscillator is varied, keeping its amplitude of oscillation constant. The amplitude of oscillation of the trolley is seen to vary. The amplitude is a maximum at the frequency calculated in B. So we switch the oscillator on, and the frequency of the oscillator is varied. So we change the frequency of the oscillator, and the amplitude of the trolley also varies. So this oscillator here, this thing begins to move back and forth. And it starts to affect the oscillations of the trolley. And the amplitude of the oscillations of the trolleys varies, but has a maximum value when the frequency is the frequency of B, 2.8 hertz. Do we know a name for the effect that gives rise to this maximum? Is there a name for a phenomenon that allows the amplitude of something oscillating naturally to increase when a driving frequency is added to its oscillations? And that we know is resonance. Resonance occurs when a driving frequency matches the natural frequency, which in this case is 2.8 hertz. And at 2.8 hertz, when the oscillator is moving at 2.8 hertz, the amplitude of the oscillations become larger. Now we're told that at any given frequency, the amplitude of the oscillation of the trolley is constant. Explain how this indicates that there are resistive forces opposing the motion of this trolley. Now, remember that the oscillator is constantly moving. It's constantly taking energy and supplying energy to the trolley, to the springs in the trolley. So the oscillator is continuously supplying in energy, or I can say supplies energy continuously. So what you'd expect from the amplitude, since the amplitude is related to the energy of the oscillations of the trolley, the amplitude should increase continuously, because there's continuous supply of energy coming in, so its energy should continuously increase. But since the amplitude remains constant, we know that energy must be lost. So when we have a driving frequency causing something to oscillate, we expect that as long as the driving frequency, as long as the driver is continuously supplying energy, the amplitude should increase to infinity. But that isn't the case naturally, and that's because energy is lost. So there's some resistive force that's providing some damping as the energy is being provided. And so if we have a constant amplitude after driving forces applied, then we are losing energy due to some resistive forces. So energy must be lost. So another interesting question And this was I forgot to state the question, but this question was from summer 2021. This was question paper 4, variant 3, and this was question 3 from that paper. That was the next question. And so the following, that question was 8 marks, also quite a common type of question. What happens when we have a driving frequency matching the natural frequency? We have to make some mention of resonance. We haven't really spoken about damping all that much so far. The next question is from the summer being November, December, summer of 2020. It's question paper 4, variant 1, question 3 from that exam paper. We're told that the piston in the cylinder of a car engine moves in the cylinder with a simple harmonic motion. The piston moves between a position of maximum height in the cylinder to a position of minimum height as illustrated in the figure. The distance moved by the piston between the positions is 9.8 centimeters, and the mass of the piston is 640 grams. At one particular speed of the engine, the piston completes 2,700 oscillations in 1 minute. For the oscillations of the piston in the cylinder, determine the amplitude. Okay, so we can see that the total distance from maximum height to minimum height is 9.8 centimeters. So if the equilibrium position is somewhere in between, then the amplitude would be half that total distance. So half of 9.8 centimeters, the answer is expected to be in centimeters. Half of 9.8 is 4.9 centimeters. So simple, I can just write that down, it's worth 1 mark. What about the frequency? Well, the frequency I measure in per second, but I'm told that there's 2,700 oscillations happening per minute. Now, frequency is the number of oscillations per second. The number of oscillations is 2,700, but that happens every minute. So I need to divide that by 60. And so what I get is the frequency is 45 hertz. And so also, quickly, I can simply write this down. If I do this in the calculator very quickly, 2,700 divided by 60 is 45 hertz. So 45 of the up and down and back to the up position motions every second. Lastly, we want to find the maximum speed of the piston. Now the linear speed, we remember the maximum speed is the displacement, the maximum displacement, the amplitude, times the angular frequency. V0 is x0 omega. I know the frequency, so I can replace omega with the frequency. So this is 2 pi times the frequency times the amplitude x0, which is 2 pi, and I want this in meters per second, so I have to convert my amplitude to meters, times the frequency 45, times the amplitude 4.9 times 10 to the minus 2 meters. And what I get is 13.9 meters per second, or to two significant figures, 14 meters per second. Next, we get a bit of a tricky question. They say, what is the speed when the top of the piston is 2.3 centimeters below its maximum height? Okay, so if I have my, I'm just going to draw a rough sketch here. If I have my equilibrium position, the midpoint of the cylinder, then, and the maximum, the amplitude at the top will be x0. And the center of my piston, I'm just going to draw it as a line, is at the amplitude minus 2.3 centimeters. So what it means is that it's 4.9 centimeters, which is the total distance, minus 2.3. And so from x is equal to 0, rather, from the equilibrium position, the piston is at 2.6 centimeters. Remember, we always measure displacement from the equilibrium position. So that distance is 2.6 centimeters. That's the displacement. Why do I know this? Because I need to calculate speed, and I need to know the speed in terms of the position. Well, I have an equation for this. V is equal to omega times the square root of x naught squared minus x squared. And omega is 2 pi f. So that's 2 pi times the frequency 45 hertz multiplied by the square root of the amplitude squared, 0.049 squared minus 0.026 squared. So if you use 0.023, you wouldn't be calculating the displacement. You'd be calculating the distance from the maximum height, from the amplitude, which would be the incorrect displacement. And so the speed I'll calculate to be, it must be less than the maximum speed, obviously, 11.7 meters per second, or 12 meters per second. So this is a very mathematical question thus far. And the last question is very much the same. We are told that the acceleration of the piston varies, as is normal with simple harmonic motion, and we want to determine the resultant force on the piston that gives rise to its maximum acceleration. We know that resultant force is, by Newton's second law, m times the acceleration, and the maximum acceleration will give the maximum force, the resultant force. And so this is m times a naught. Can we write a naught any differently? Yes, m times omega squared x naught. I can ignore the minus sign here. I just want the magnitude of the resultant force. I know the mass of the piston is 0.64 kilograms multiplied by 4 pi squared times the frequency squared, since omega is 2 pi times f, times the frequency, which is 45 hertz squared, multiplied by the amplitude, 0.049 meters, and we get the net force to be 2.51 times 10 to the power 3 newtons, or 2,500 newtons to two significant figures. And so this question was almost all, actually, was purely mathematical, just calculations all the way through. So you need to know your expressions, like the expression for velocity, for speed in terms of position. I think that one is in the formula sheet, but you have to make sure you go and check what equations are there, what you need to remember, how to rearrange them, and so on. But remember, we have equations for speed in terms of time and speed in terms of position, and you need to understand them all and where to apply them and how to apply them. And so this question was a total of 9 marks, and you could have done it relatively quickly. Again, it depends how comfortable you were with the mathematics. The next question is number 87, and this comes from the March 2019 exam. This is question paper 4, variant 2, question 3 from that paper. So we are told that a cylindrical tube seal at one end has cross-sectional area A and contains some sand. The total mass of the tube and the sand is m. The tube floats upright in a liquid of density ρ, as shown. The tube is pushed a short distance into the liquid and then released, and we are told to state two forces that act on the tube immediately after it's released. So what we'll find is that this tube will undergo simple harmonic motion. It'll bob up and down in the liquid. So what are two forces that act on the tube immediately after the tube is released? So immediately we know that the weight of the tube will act downward, vertically downward. But the tube bobs up and down, so there must be an upward force. But what we know is when we place an object in liquid, there's going to be a buoyant force or an upthrust due to the liquid. And so the two forces, you're only asked to state the two forces. One will be weight, the other will be the buoyant force or the upthrust. So that acts on the tube as after it's been released. We are then told to state and explain the direction of the resultant force acting on the tube immediately after it's released. Remember, after the tube is displaced downward, the tendency of the tube is to bounce upward. And so if it's moving upward, the resultant force must be pointing upward. Acceleration is acting upward. So the upward pointing force must be greater. And so I must explain why I say that as well. And so the upthrust is greater, I'm doing my explanation first, then the weight. And so the resultant force is upward. The upthrust is greater than the weight, and the resultant force initially is upward. Next, we are told that the acceleration of the tube is given by the expression A is minus A rho g over m times x, where x is the vertical displacement of the tube from its equilibrium position. We need to use this expression to explain why the tube undergoes simple harmonic oscillations in the liquid. So firstly, actually, let me write this down in a way that I'm more comfortable with. A is minus omega squared x. The omega squared ensures that that thing is always positive. And so there's a minus sign in front of a positive number. So I have to make sure that everything inside the bracket is positive, because I'm not squaring anything, so it must all be positive. But what I can see is that A, rho, G, and M, A being cross-sectional area, rho being density, G being the free fall acceleration, M being mass, these are all positive numbers. These are all positive values. And so these are, I'm going to say, positive constants. So I'm kind of killing two birds with one stone there, but these values are all positive constants. So what it means is you should be saying acceleration. I'm too lazy, so I'm just saying A is proportional to x. Since all of these values are constants, they are proportional to x. And since they are positive, then the minus sign, the negative sign in front of the brackets, ensures opposite direction. Ensures that they are in opposite directions. So they are constants, and hence A is proportional to x, and the minus sign ensures they are in opposite directions. I added that they are positive constants because, man, the positive constants means they are definitely in opposite direction to, or A is definitely in the opposite direction to x, because the signs will always differ. Okay, so that was a 2-mark question. Next, we are told that for a tube having cross-sectional area A of 4.5 square centimeters and a total mass of 0.17 kg, the period of oscillation is 1.3 seconds, and we have to determine the angular frequency of the oscillations. Well, this, without any trouble, we can see angular frequency omega is 2 pi divided by t, which is 2 pi divided by the period of 1.3 seconds, which is an angular frequency of 4.83 radians per second, or to two significance figures, 4.8 radians per second. We're then told to use our answer in 1 and the expression in B to determine the density rho of the liquid in which the tube is floating. So like I said before, the thing in the brackets is omega squared. So that's A rho G over M, which means with a quick change of subject of formula, rho becomes m omega squared divided by A times G. And so this is 0.17. The mass m is given. Omega we've calculated, so that's 4.83 squared divided by the cross-sectional area, 4.5 times 10 to the minus 4, because I have to convert that to square meters rather than square centimeters, and G is 9.81. And so what I get is 8.98 times 10 to the power 2 kg per cubic meter. Or again, to two significant figures, 9 times 10 to the minus 2 kg per cubic meter. And so that's the density of the liquid that we have, 9 times 10 to the minus 2 kilograms per cubic meter. And so if you ever needed to find a constant, you can, usually that constant will be within the brackets. That is, the constant will be equal to some combination of variables that are equal to omega squared. And so you can rearrange and solve for that constant. In this case, that constant was rho, was the density of the liquid. And so that was a nice long 10-mark question, but we did it in fairly short time. The next question is number 88. And again, the subject code is 9702. This is from the winter May-June exam 2019. Question paper 4, variant 1. And this is question 4 from that paper. We are told that a mass is suspended vertically from a fixed point by means of a spring. This is a common type of oscillation problem. The mass is oscillating vertically, and the variation with displacement x of the acceleration a is shown in the figure. So a nice straight line graph, almost a nice straight line graph. Something is a bit wrong here. And we first want to state what is meant by the displacement of the mass on the spring. So displacement, we know what it means in general kinematics, but what does displacement mean for oscillatory motion? The distance, specifically displacement of this mass on this spring. So displacement is the distance of the mass from equilibrium, from the central point, in a given direction. We must include in a given direction because displacement is a vector. So we need to have a plus or a minus sign to tell us if it's up or down from the equilibrium position. The distance of the mass from equilibrium in a given direction, and that's displacement. Now the next question says, suggest how figure 4.2 shows how the mass is not performing simple harmonic motion. So if you look at the graph, the only oddity of this graph is the fact that it's almost a straight line, but it's not a straight line. So you could sort of, I wouldn't say guess, but you could make an educated guess about why the object is not undergoing simple harmonic motion. We know that simple harmonic motion requires the acceleration a and the displacement x to be directly proportional. Direct proportionality demands that we have a straight line graph passing through the origin. We don't have that. So we can see that at some point here, maybe, the graph ceases to be a straight line anymore. It starts to curve. And so a and x are not proportional at those points, and hence they are not proportional, because that's not a straight line. So how do we know from the graph that the mass is not performing simple harmonic motion? I'm going to say that the graph is not a straight line. Simple and straightforward. We are told that the amplitude of oscillation of the mass may be changed, and we want to state the maximum amplitude, x0, for which the oscillations are simple harmonic. So if we reduce the amplitude from what it is here, we might get a straight line oscillation. And so we want to know the amplitude if the graph is going to be straight. And so what I'm going to do is I'm going to read the point off on the graph where I've drawn the x, where the straight line begins to curve. And what I find from this point is this point in which the graph is more or less a straight line is 0.9 centimeters. Or they'll also allow 0.85 centimeters. And so the maximum amplitude to keep the oscillation simple harmonic is 0.9 centimeters. Next, we are told that for the simple harmonic oscillations of the mass, we are to use the figure to determine the frequency of the oscillations. They asked me to use the figure, and I know I'm going to need to use a equals to minus omega squared x. How do I know that? Because I'm given a graph of a versus x. And so the one thing that I can find from the graph, or one thing that I will be not determined from the graph will be omega, and omega is related to the frequency, so I can find the frequency. So what I'm going to do is I'm going to choose a random point on the graph. I can choose any point on the graph. And I'm going to choose the points where the displacement is minus 0.75 and the acceleration is 1. And if I put these into the equation, I also got the acceleration is minus 4 pi squared f squared times x. That means the frequency is the square root. Again, I like doing a lot of extra math. If you want to put your values in earlier, you can, but I feel this way just saves a bit more time in the long run. A over 4 pi squared x, and this is the square root of minus, acceleration is 1, divided by 4 pi squared, and the displacement is minus 0.75, converted to meters, times 10 to the minus 2. And we get a frequency of 1.84 hertz. Two significant figures, this frequency is 1.8 hertz. So you can choose a random point from the graph, substitute it into the equation, and then solve for frequency. So we've done questions like this before, but here there's an added step of complexity because you need to choose points from a graph. It's not difficult, but there's an extra step in which you could possibly make an error, reading from the graph, etc. So my suggestion would be to take a point from the graph, plot it, look at it, make sure that you've done it properly and you have the correct units as well. We are told then that the maximum speed of the mass when oscillating with simple harmonic motion of amplitude x0 is v0. And we want to show on the figure the variation with displacement of the velocity of the mass for displacements from x0 to minus x0. Now we should already know that the graph of velocity versus position is going to be elliptical or circular, depending on how our object is moving. Some sort of ellipse. And so my maximum velocity happens when there's no displacement, happens to the equilibrium position. And so when x is equal to 0, I have the maximum velocity. But the object could be moving in either way. It could be moving up or could be moving down. So when the displacement is 0, I could have velocity positive or velocity negative, but it will be maximum in magnitude. Similarly, at the amplitudes, there is no velocity. The object is changing direction, so it momentarily comes to rest. So either position at the amplitude or the negative amplitude, velocity is 0. And so what we see is I drew 4 points, but I need to connect these 4 points. And the only way I can connect these 4 points is by drawing an ellipse. So obviously you can't do what I've just done. That is, just get a circle and drag and drop it in. But you would draw this with a pencil, marking those 4 points and drawing your line or drawing your ellipse or circle through those 4 points. And so your graph would look something like that. Obviously, again, you drawing it in pencil, make sure the graph is curved and don't draw the points with a straight line, because we know that if I write the equation out mathematically, it's not a diamond shape, it's not a rhombus, it is a circle or an ellipse. And so you need to plot your points and then make sure you draw a nice freehand ellipse as best as you can. And so that will always be the shape of a graph of velocity versus position for simple harmonic motion. So the first time we've seen that graph, actually quite interestingly, we haven't seen this graph yet, but it is one that comes up often when you're answering these past exam papers. Now the last question we are going to do is question number 90. And this question comes from the summer 2018 exam. It's question paper 4, variant 1, and it's question number 2 from that paper. We are told that a vertical plate is made to vibrate vertically, rather a metal plate is made to vibrate vertically by means of an oscillator. So we have an oscillator causing the plate to vibrate, and we have some sand sprinkled onto the plate. The variation with displacement y of the acceleration a of the sand on the plate is shown. So we can see a nice straight line graph. There's no kinks in this graph. It's actually a nice straight line. And we want to show how it can be deduced that the sand is undergoing simple harmonic motion using this figure. Now again, we need to say for simple harmonic motion that A and Y are proportional and in opposite directions. So I can't simply say that, I have to state that with reference to the graph. How do I know that things are proportional when I have a graph of two things drawn straight line through the origin? That indicates proportionality. So that indicates acceleration proportional to displacement. Again, you're going to write this in a full sentence. I'm writing this in a short form. So the straight line through the origin indicates that acceleration is proportional to displacement. The other thing is that the acceleration and displacement must be in opposite directions, which means the gradient must be negative. But that's exactly what I have. So I can simply say the negative gradient shows that I can say they because I refer to them already, they are in opposite directions. So the straight line to the origin indicates that they are proportional, because that's what proportionality means, and the negative gradient tells us that they are in opposite directions. And those are the two conditions for simple harmonic motion to occur. So another interesting type of question, in this case we have a graph rather than a mathematical expression, but we can still explain it in the same way just by referring to the graph. We're then asked to calculate the frequency of the oscillation of the sand. Again, I'm not given any values, but I'm given a multitude of values, which is basically what my graph is. And I'm going to again just take two random points. I'm going to choose the points where the displacement is 6 and the displacement is given in millimeters, or 6 millimeters, and the acceleration is 3.4 meters per square second. And again, I go A is minus omega squared x, which is minus 4 pi squared f squared times x. Don't forget that omega is 2 pi f. The angular frequency is 2 pi times the frequency. And so f is the square root of minus a divided by 4 pi squared x. I can now put in my values. I can take the points I've chosen, which is minus 3.4 meters per square second over 4 pi squared, and the position at that point of the displacement is 6 times 10 to the minus 3, because we have to convert this to meters. And what we get is a frequency of 3.79 hertz. Again, the two significant figures, 3.8 hertz. So simply we can calculate the frequency of oscillation for the sand. Part B is something different. It says the amplitude of the oscillation of the plate is gradually increased beyond 8 millimeters, beyond the maximum that it was, and the frequency is constant. At one amplitude, the sand is seen to lose contact with the plate. And for the plate, when the sand first loses contact with the plate, state the position of the plate. So if the sand loses contact with the plate, where do you expect this would be? Well, it would obviously be when the plate starts to suddenly move downward. Right? And where does the plate suddenly move downward? Well, the plate suddenly moves downward at its maximum upward displacement. Or you could say the maximum highest position above equilibrium would also be acceptable. I'm going to say it's at the maximum upward displacement. So the plate begins to accelerate downwards, accelerates downward quicker than the sand can do so, and so it leaves the sand behind for a moment in time, and the sand loses contact with the plate. And so that point will be the maximum upward displacement. And for the time when the plate first, or the sand first loses contact with the plate, we are asked to calculate the amplitude of this oscillation. So how do we know when the sand loses contact with the plate? So remember, the sand is going to leave the plate when the downward acceleration, the maximum acceleration, which happens at the highest point, is equal to g. So the plate begins to move downward, and for a moment in time, the weight of the sand and the force downward is the same, and so the force F is equal to the weight of the sand is equal to mg. And so the plate accelerates downward at the same speed that the sand does, and for a moment in time, the plate and sand are just separated. And so this means that the acceleration A is the free fall acceleration g, which means g is equal to minus omega squared times the amplitude y naught. And so y naught is equal to minus g divided by 4 pi squared f squared, and this is minus 9.81 divided by 4 pi squared times 3.8 squared, and I get this to be, I can drop the minus sign, I'll write it down for now, minus 1.72 times 10 to the minus 2 meters. But the answer does ask us for millimeters, so the amplitude of the oscillation, I can drop the minus sign, will be 17 millimeters. And so that's the amplitude of the oscillation for the sand to leave the plate. So we need quite a high oscillation, and for that we need a very strong force. We're having a very high amplitude, meaning we have a very strong restoring force, and the sand can eventually leave the plate. And so that was the last question for this part of the problem solving video on oscillations. The next video I will continue doing some oscillations questions, and then we'll move on to other topics, and I'll try to get to other papers as well as much as I can before your exams. I hope this video was helpful. I hope that you're studying well and you find these topical past paper problems useful. If you do, please leave a like, comment, subscribe to the channel if you haven't already. Let me know if you have any comments or suggestions. But that's all for me, Mr. K, for now. I'll see you again next time when everything is relative.